Hello everyone, I'm Dr. Angshuman and I'm very happy to be part of this great generative AI event. Thank you Samir, Bhaskar and Nanda for having me and for organizing this great conference on generative AI. So today in this event, I'll be discussing about GAN or Generative Adversarial Network, starting with some background, how GAN works and some applications of GAN. So let's go to actual technical things. Let's try to start with a fun example, right? And this is the example that I used in one of my class that I was teaching at one of the top institutes as well. So on this screen, I show you three pictures, three human images, A, B, and C. So can you see the picture and tell which of these is real? Just take few seconds, note down your answer, and then I'll give the actual answer, right? So I tried in the class and nobody could give me correct answer. So the correct answer is B. No, not B. Actually, the correct answer is none of these faces are real, right? All three of them are generated by AI. So it is really fascinating, isn't it? Now let's try to see a video. So this is a video of Morgan Freeman. You'll be probably able to see the video and I hope you'll find it interesting. So this is also an application of GAN to create something that doesn't exist in terms of image or video or audio. Now coming to actual GAN, what it is and how does it work. So GAN is basically a type of neural network. The full name of GAN is Generative Adversarial Network, GAN. So this is a class of machine learning framework that is extensively used for generative AI. So now generative AI has become very popular, right? But when people think of generative AI, everybody thinks of ChatGPT. But no, ChatGPT is not the only generative AI, right? So you have GAN, which is very powerful, especially for tasks where you need to some generative AI, but in terms of image, audio, or video. This concept is not actually new. It was first introduced in 2014 by Ian Goodfellow and his colleagues. In case of GAN, instead of one neural network, there are two neural networks, and these two neural networks compete with each other, right? And that's how we do the training and create the output. So these two neural networks are called, one is generator, other is discriminator. We'll discuss about them in more detail in a later slide. Before you go to the neural network architecture of GAN, let us try to get some intuitive understanding how GAN works, right? So do you know the picture on the left? I'm sure most of you will know the picture. It's one of the most famous paintings called Mona Lisa by Leonardo da Vinci. Now let's take this situation. So this painting is very famous, and in the auction market, this painting will probably sell for millions of dollars. Now, since it is valuable, there will be a lot of forgers who will try to create fake Mona Lisa. Let's assume that we have such a forger who is trying to create a fake Mona Lisa painting. But if he's trying to create the fake Mona Lisa painting, it will not be close to real, and anybody can tell, hey, it's not real, right? So it will probably have no value. But suppose he becomes better at his trade and creates a better forgery. And now we hire a detective whose job is to find the painting is fake or real. And the detective is an expert in art and especially painting. Now, every time the forger creates an image of Mona Lisa, the detective tells it is real or it is fake, right? But forger also gets to know about it. And once he knows that detective has identified the fake, he tries to create a better fake which is more closer to original. Now, initially, the image will not be very close to real, but if we repeat this process hundreds of times, thousands of times, or more, after a point, probably the forger will create such a good image which will be so close to the original that even the detective cannot find it, right? So finally, we'll be able to create a fake Mona Lisa which will be as close to real that humans can't identify whether it is real or fake. So that's the intuition behind GAN. Now let's see how it actually works in the neural network context. So in the neural network context, we don't need to give an input to create this kind of output. We can give some noise vector as the input, and we have a neural network which is called generated, and it creates some generated sample, right? Very simple. However, there is a big problem here that once the sample is generated or data is generated, we don't know that it is real or fake and how good it is, right? So you have to have some mechanism to make sure the output is very close to real. And that's where we bring in the second part of the architecture, which is called the D or discriminator. So this is again a neural network. The D neural network or discriminator gets two type of input. One is the output generated by generator, but it also gets a sample of the real data, right? Now, if it gets some generated sample as well as real sample, it can compare the two and tell which is real, which is fake. So that's the output of discriminator. Now, based on this, we can find out how good the generated samples are. And this is the loss function that goes back as a feedback loop. And just like the intuition that I explained in case of Mona Lisa painting, the same process is repeated time and again, hundreds and thousands and more time. Every time generator creates something new, discriminator tries to tell it is actually real or it is fake. And if we repeat this process, every time discriminator can identify the image, the generator creates a better image, more realistic, even more realistic, right? So after a point, we cannot tell the output from generator is real or fake, right? Even humans not tell it. So that's how the training happens. Now let's see how this exact concept can be used to generate portraits of human face. That is a very interesting application of GAN. So instead of generating just another random, so here if you see the image or the diagram on the left side, we take some random noise as the input. We have a generator, but in case of actual neural network, this is a neural network. This is not actual human being, but it's a neural network. So this neural network takes in the random noise, and based on that, try to generate some portrait of human face. And just the earlier example, we also put a discriminator network, which is again a neural network, whose job is to find out these generated photos are actually human face or not. And based on this comparison, discriminator will tell it is real or it is fake. And just like the earlier example, you repeat this process time and again. So after a point, discriminator cannot tell the image generated by generator is real or fake. And that means you have generated an image which is very much like real and which can be used as an image. Now we have understood GAN. We have understood the neural network architecture basic for GAN. We also saw an example of GAN. So now I will discuss two specific variations of GAN, which are also very interesting and can have very good practical applications. So those two variations of GAN are cycle GAN and style GAN. So let's start with cycle GAN. So cycle GAN is also a GAN. It's a GAN which is used for performing translation between two domains, domain A to domain B, and vice versa. So example can be domain A is horse, domain B is zebra. So how do we take picture or video of horses and convert it to zebras? Another example can be photos of night and day, right? So between night and day, there are differences between light of other things. So how do we convert a photo which is night photo to a day photo and vice versa, right? So how does it work? Now let us focus on the diagram on the right and first focus on the top right part. So we start at the top where we take an image, which is the input horse image. Now this image goes to a generator network, just like we have seen, and it tries to create a zebra image. So domain A to domain B. Domain A here is horse, domain B is zebra. And we use another generator network to convert domain B to domain A. So the main difference that you can see from GAN to cycle GAN is that in GAN it was one directional. From domain A I create domain B, but here from domain B I try to recreate domain A image. So from zebra image, again another generator is creating a horse image. Now let us focus on the bottom part of the diagram. From the So here the zebra image becomes the input image starting point at the bottom. From that generator creates a horse image, and from the horse image another generator creates a zebra image, right? Now we have two discriminator here, one discriminator for domain A on the left and one discriminator on the domain B on the right. So domain A discriminator takes the original horse image and then generated horse image from the bottom and tries to tell it is real or not. And on the right, discriminator B for domain B zebra, it takes two zebra image. One is original, other is generated and tells it is right or not. So basically, we have two discriminator for domain A and domain B. And we again repeat the training process just like we discussed earlier. So after a point, the network will be trained and we can give any horse image and it will convert to zebra image and vice versa. So let us see an example of it. So if we see this example, and these are actual examples generated by CycleGAN. So on the top half, we are showing conversion between horse to zebra. Then we show zebra to horse, right? So it can transform images from domain A horse to zebra and vice versa, zebra to horse. And you can see the images retain all other features of the image, including the background, the size and everything. Just horse is converted to zebra and vice versa. The bottom one, another very interesting use case or application of CycleGAN, which is from apples to oranges and vice versa. So you can see, you can give any picture of apples, whether there are few apples, lot of apples, or maybe you see some apples in the actual apple tree, and use CycleGAN to convert all the apples to oranges. And similarly, if you have orange pictures, you can convert to apples. So these are two examples, but it can have other interesting use case. It just depends on your imagination. One example can be popular face app, where you have a photo, you add some smile or some style to the photo. Or we also have other use case where you apply the style of a painting on a photo, right? You want to create a photo on the Van Gogh style. Now last example that I want to show you is about the style GAN. So style GAN is another variation of GAN. So this was launched by NVIDIA in 2018, and style GAN 2 was launched in 2020 and 3 was launched in 2021. So it has been there for a couple of years. And style GAN architecture is a bit more complex than the other architecture that we have seen. So we'll not get into detail of it. If you are interested, you can read the original research paper and try to implement it. But the basic idea is that in addition, we are adding a style block, which is the square box that is shown on the picture on the right, where we take some input, do some transformation on it, add some convolution, add weights, biases, then add some Gaussian noise, and then normalize. So basically, we are doing certain special processing, which we call style block, to create a different kind of output. So what style GAN can do is even more fascinating. So let's see the example. So this is exactly what we saw on the first slide. So in case of cycle GAN, we take from one domain picture, create another domain picture. Some parts we still retain, right, between those paired pictures. But in case of style GAN, we can create completely something new which doesn't exist in reality. So first slide, we saw some images of human portrait which don't exist in reality. And similarly here, this is from the actual style GAN paper. You can see, almost face generated by style GAN, and none of them exist in reality, right? So again, style GAN can be used to create a lot of new things. I showed you example of a human portrait, but it can create also, videos or audios or other kind of, content. So the limit is only your imagination. So with that, I'll end my presentation. Hope you learned something new and found it interesting. All the best. Thank you.
Thank you so much, Angshuman. Really appreciate you have a knack of being, if not a professor, and a professor with a mass following, a following which can actually surpass many of the celebrities. So thank you so much for the opening session. Really appreciate. Bhaskar, your take on this session.
Yeah, I think excellent. The way Anshuman presented the whole concept, I absolutely loved. And especially maybe one thing that I am taking away, the whole example of a forging agent and a detective. That is a classical way in which the whole concept of GANs works. And that will remain with me, and I'm sure with others on the session today forever, as a way of explaining how the whole process is being executed in the background. Now that is one. Second, of course, a lot of applications that we get to use today, be it applications like Prisma, which came out a number of years ago, or the ones that are there in the market today, which people can download from the App Store. They are using variations of what Anshuman spoke about as a cycle GAN or a style GAN. These are picking up very narrow applications of what is possible using GANs and applying that to our day-to-day objects. So that I think was my key takeaway, Samir.